All right. So we're talking about a bunch of different sound and waves properties. We got some different examples though. Transverse waves, and we were just looking at springs in the hallway here that were demonstrating transverse and longitudinal waves. But transverse waves is something that shows up in lots of different places. And I don't know like what you know, but hopefully you know what this is supposed to be a cartoon of. Yeah, it looks like it's a guitar or something. It's got 6 tuning pegs, so it must be. If it was 4 tuning pegs, what would it be? Could be a bass, could be ukulele. Okay. But when you pluck on a guitar string, what you're really doing is you're creating a pulse, right? But then that pulse translates into a wave, and that string resonates. But the type of pulse you're making, is it a transverse or a longitudinal? Transverse is back to back, right? Or back and forth. If you find yourself, you guys tell me what this is. This is my quick little sketch. I don't know. What is this? Yeah, some sort of speedboat. Anytime you find yourself on the water, you're dealing with transverse waves. I mean, likewise, though, when you're seeing this boat from overhead, let's just say that this is the overhead view of that exact same boat. Well, how would you illustrate the waves? See how there's a peak here? We represent it with wave fronts. So the peaks are represented as lines on an overhead view of waves. I think that makes sense too, right? This is just a different perspective on the exact same scenario. But these guys are different ways of illustrating transverse waves, a transverse pulse. And we done it earlier with slinkies or springs. Longitudinal waves, we've talked in the past about this idea of, longitudinal wave doesn't look like that, but if we actually say that this is a density graph of what's really happening, like in the case of air particles, we'd say that we have dense air particles. And remember the rarefaction regions, that's the low density air particles. And then the compression regions, the high density particles, followed by another rarefaction. And this idea of the stippling that we learned in art class feeding into the idea of relative density illustration. So we talk about compressions and rarefactions for these longitudinal waves. And of course, we illustrated those with slinkies as well. Then there's this idea of interference, and we tried to illustrate that with slinkies out in the hallway, with springs sending positive and negative pulses. But I want to kind of think of it more graphically for a second, like a graph. If I were to have a graph of a wave, and the wave looks like this. Now, depending on where you're at with your math right now, you might have talked about function notation, f of x. Raise of hands, how many people have talked about function notation? Right, about, as I suspected, about half the room, okay? That's semester 1. Semester 2, everybody will have talked about it. So it's not like it's something that's not coming for you, okay? But if this is our graph, and those of you who haven't heard of f of x notation before, doesn't matter. We're just saying it's a graph, okay? So we got this graph of a wave, and we're going to take another graph of a wave. Different wave, mind you. Turns out that if I take these two graphs of waves, it's possible that 2 different waves get produced at the same place at the same time. Agreed? That makes sense? We talk over each other all the time. That's multiple waves happening at the same time, right? And so it makes sense that we must be able to have some sort of graphical description of what the superposition or the multiple waves at the same time happening looks like. So we could say, if that's f of x and this is g of x, in other words, this is just wave 1 and wave 2, if you want to talk that way, because you haven't encountered that notation before. Doesn't matter. Wave 1 and wave 2, okay? I even called them that, wave 1, wave 2. We could have wave 1 plus wave 2. Or those functional notation people would say f of x plus g of x. Okay? And people say, well, how would I add these up if I don't know what the equation is? Oh, let me tell you. Superposition is a magical thing. What you got to do is you got to take slices. And I feel like we've been in the zone where we have sliced graphs up before. This was a graphical modeling tool that we used earlier. I'm not talking about kissing the curve or tangents or anything. I'm talking about slicing. Instantaneous slices. And if I take a bunch of slices of these two graphs, the reason I would do that when I have these graphs stacked on top of each other is to say, hey, at this moment in time right here, if these two graphs are adding up with each other, can you see that I would add this height plus this height? And I wish I had a grid in the background, but it would add up to being about this height. For the next slice, I'd say, oh, okay, well, this height, I could even use a millimeter scale if I want to. Oh, looks like I got about 2 millimeters, 4 millimeters. All right, I got up to about 6 millimeters. Got about 3 millimeters, 5 millimeters, 8 millimeters. You know, I could go along, if I wanted to be super particular about this, I could keep on adding up like that, and I could keep on figuring out what these slices are going to sum to. And let's just say that I did it. I added these guys up all the way along. Next slice. Ooh, the next slice, look, see how there's a negative amplitude here, but a positive amplitude here? Oh, this one here was 0 and a positive amplitude. All right, so 0 plus something is something. But negative plus positive, that actually would cancel each other out. That would be a 0. If it was the same magnitude negative as positive. This one here is a bigger negative and a smaller positive. Oh, okay, so we're going to dip negative on that one. Nice big negative and almost 0. Negative and just barely 0. Maybe even more negative. Little bit of positive, little bit of negative. Ooh, interesting. 0's out again. See, a little positive, little negative, just to be just about 0. Maybe it's a little more negative than positive. Remember, I'm being kind of qualitative at this point because I really would like to have a grid in behind if I want to be even better about it. This is just an introductory little explanation of superposition, okay? Then we say positive, negative. Oh, this one's slightly more positive than the other one is negative. Positive, negative. Oh, a little bit more positive than negative. Positive, negative. Still a little bit more positive than negative. Oh, and now they're both 0. All right. Now you say, okay, well, we've done the superposition of these two functions, these two waves. What are we going to do next? It rhymes with nerve of fest bit. Curve of best fit. Yes, you're right. Okay, so I'm going to have a curve of best fit here. And people say, really? That's the curve that you end up getting out of those two functions? Well, yeah, that's okay. That kind of thing happens sometimes. And it happens with voices all the time. In fact, like, I don't know how I can illustrate this. Let's see. I got this visualizer here, and you can see on the little green graph. Can you see my voice on the little green graph? Right now, that graph looks really ugly. You see how it's all jittery and everything? Kind of like the graph that we just produced here is all jittery and everything. But listen, I'll try and make like a nice clean tone. See how it came like really close to looking like a sinusoidal wave? I mean, even if I want it to be better, I don't know if it'll pick up my tuning fork. Let's see. Nah, my tuning fork doesn't have enough amplitude. But let me think. Where can I get a nice tone from? Maybe I have a tone generator on my phone. You know, there are some nice tone generators for download, and where is one that I can choose? Here's one. All right, so this is a frequency sound generator that I picked up off of the App Store. Let me turn up the volume a little on this. It's not loud enough for me. There we go. If I turn the volume up, can you see the waveform that's on the green graph? Now, some people have noticed the bottom graph is actually a frequency scale graph. Can you see the horizontal line on the frequency scale graph? That's the frequency that I'm playing. And if I change the frequency, that bottom graph jumps up, right? We also notice that on the little green graph, the waves get smaller. Let me stop talking so you can see it. See how the wavelengths are shorter when the frequency gets higher? If V equals lambda F, that must be true, right? Frequency higher, wavelength slower, because the speed stays a constant speed of sound. Listen to that again. I'll knock it down because this is hurting my ears. I'll take it down to a lower frequency. Seems like my microphone doesn't want to pick up lower frequencies. It only likes the higher frequencies. But I think we get the idea, right? So we get the idea that higher frequencies are going to make shorter wavelengths because the speed is a constant. We have the idea that we have these sinusoidal waves, and my voice wave that you can see right now clearly is a combination of my throat resonating, my sinuses resonating, my chest resonating. It's actually a bunch of waves being stacked on top of each other to make that ugly graph that you see, right? And we can argue about whether my voice is beautiful or ugly, but the graph certainly is, okay? It's an ugly graph because it's a superposition of a bunch of different sound waves, all superimposed on top of each other. All right, let's take that out of the way. We may or may not come back to it later. And then I also want to make sure that we get this idea that when we have a ripple, imagine this is a ripple on a pond. Earlier I said that when I take a look at transverse waves from overhead, like on a boat, we do the wave fronts like this. So this would be the wave fronts around a circular source. And I want to make a couple points about this. Circularly expanding waveforms are seen on water. I'm going to say often seen. On water when a stone is dropped in. Sure, why not? Now, that's easy to picture. But we can say we infer that a point source of sound creates a spherical wavefront. Most of us don't have a problem picturing a circular ripple. Everyone's thrown a rock into a pond or something like that, right? A spherical ripple, that means that if I have somebody named Rebecca standing right here and she just starts talking, she says, "Hey, get over here." The ripple doesn't go out like a circle. The ripple of her voice goes out like a sphere in all directions. And if I want to make it look all spherical, I'd have to like add some sort of three-dimensional contour lines or something to make us believe that that's a sphere. And this looks messy in a hurry. And the fact that it looks messy in a hurry, I think even in a simple stick person drawing like this, explains to us why we have a hard time picturing it, right? It really does get messy in a hurry. If you find a nice textbook where each bubble has been watercolor painted a slightly different hue, I bet you can picture it ever so slightly better. But if you can picture like chicken wire frame spheres, concentric spheres, as spherical ripples, then you've already got that in your imagination. How many people feel like they have it in their imagination? A lot of the hands go up. Okay, so I bet you we could find a prettier illustration, but if we got the idea, then we got the idea. Okay, so spherical ripples are a thing, and your voice right now, like, listen to this. I'm about to make a spherical ripple. Hoot, hoot. Oh baby, but you can't see it. That's the problem. We can see the ripple on the pond, but you can't see the spherical ripple from your voice. But it's there, and we believe in it. Okay, and that's something that we want to make sure that we can nail down. So we've actually gone from, and that's like, this is an important thing in terms of dimensionality. We have gone on this one page from one-dimensional waves on a string to two-dimensional waves on a river to longitudinal waves that we can't see in the air, talking about how multiple sounds can happen at the same time, superposition, and discussing that ripples on a pond illustrate the fact that these longitudinal waves in the air actually ripple out as spheres. By gosh, that's a lot of things. But that's sound, right? That's waves. And hopefully that makes some sense to people. There's a lot of physicality to this. Notice we haven't done a lot of math except for that graph. But I'm not even confident that is like a high level math thing if it makes sense to you, right? We're just adding up shapes.